Hi, my name's Ian. I'm a dad. I've done some business. I'm an engineer, and I've been worried about climate change. I've been worried about the lack of really massively scalable, affordable solutions. Until I've been worried until I started learning about how they're using green electricity to make green fuels. Um, and today I want to talk about green fuels and try to clarify some of what's going on, right? So this molecule here is ammonia. It is made from hydrogen, and you get the hydrogen from water, and it's made from nitrogen, and the air is 78% nitrogen. So you grab nitrogen out of the air and you use electrolysis to split apart water into hydrogen and oxygen. And part of what I want to talk about is there's a lot of discussion about hydrogen, but hydrogen you don't nobody actually cares about the atom. What they care about is the chemical bond and the chemical reaction. So let's spend a couple minutes here looking at uh, chemical reactions of hydrogen and ammonia and compare them. Um, but first, let's talk for a second about fossil fuels. So we carbon fuels, greenhouse gas. Fossil fuels, what they are is some variation on this. Hydrogen bonded to carbon. Often it's a long string of carbon. This is methane, so it's very simple and just one carbon. Um, the energy in this is in the chemical bond between the hydrogen and the carbon. Um, and the problem with this is there's a bunch of carbon locked up under the earth. And as we dig it up or pump it up and burn it, you're changing the amount of carbon in the air, right? So it's the net change in the carbon in the air that's the greenhouse gas issue. Um, if you burn a tree, the tree absorbs carbon out of the air and you burn it and it's released back into the air. Over 100 years, there's basically no difference in the amount of carbon in the air. It's the fossilized stuff, the buried stuff that's causing such a problem. So ammonia is made with nitrogen from the air, and when it is burned, the nitrogen goes back into the air. All right. So see, there's no net change. Um, and it has these chemical bonds with hydrogen, right? And that's where the energy is stored. Uh, Now, chemical bonds, each bond, chemists have spent a lot of time figuring this out. I'm not even sure how they did it, but these bonds have each bond has a sort of unique amount of energy in it. So a hydrogen to hydrogen bond, for example, has 432 kilojoules per mole. Now, mole, it's a measure of how many. It's a standard unit of atoms. Okay, so it allows you because each type of atom weighs a different amount. It's not a weight. It's like a number, right? So it's forget how many. It's thousands, but basically think of it as like it just allows you to do apples to apples, right? Now, in a chemical reaction, usually everything you start with has bonds. And then what we're doing is we're rearranging those bonds um, to create new things. And that reaction there either requires we add energy to it, okay, or it releases energy. So if you break apart water into hydrogen and oxygen, it's what's called an endothermic reaction. Endothermic, meaning it absorbs energy. So we're storing energy in those chemical bonds. We're changing the amount of energy in those chemical bonds. And so we take, say, electricity and turn it into stored chemical energy, right? And the opposite, an exothermic reaction, if you say burn hydrogen and it gives off heat, that's that energy being released. Okay, so a chemical reaction either stores energy, sucks it up, or releases energy. And I mean, we're not going to go into all of the steps because it does get quite complicated. We're just going to do the beginning and end. In between, there's a lot of steps. And like, for example, this is ammonia with a catalyst, how like the nitrogen will break apart and then some hydrogen will come along and the hydrogen will, we don't need to know this, okay? The point is green energy, green electricity can be stored chemically. So for example, if you in a water molecule, right, there's a bond between the oxygen and the hydrogen. There's two of them because there's two hydrogens, right? And each bond has 463 kilojoules per liter, right? So each bond, and there's two of them, has 463 kilojoules, okay? So if you put energy into this, you can get it to break apart. And that product then has hydrogen, okay, and oxygen. And those resulting molecules have a different amount of energy than the water you started with, okay? And the difference, the amount of energy you have to sink into this is 485 kilojoules, right? So that's sort of the math of like how much energy can you park in an atom. That's what we're doing here. And then in reverse, take a fuel cell, for example, put hydrogen and oxygen into it, and it's going to give off energy. And chemically, we know how much energy it can give off. There's going to be losses, there's going to be heat and other things, but this is chemically how much energy is stored in there is 485 kilojoules. So if now I'm going to change the number of things we're doing in this reaction. We're going to use 6 hydrogen, 3 oxygen, just to make it apples to apples later. So burning pure hydrogen, so reacting that hydrogen with oxygen to produce water, the difference on one side to the other side, the amount of energy it gives off is 1,455, so 1,455 kilojoules. If instead of doing that, we took nitrogen and combined it with hydrogen, right? So we're, instead of making water, we're going to make ammonia. There's a very much smaller difference, okay? It's 194 kilojoules, okay? So like an order of magnitude different. So this is also exothermic. It gives off some energy to produce ammonia, but not that much. And why do we want to do this? It comes down to handling ammonia versus handling hydrogen. We're giving up a little bit of energy, but now we have ammonia, which, and okay, we'll look at this. So, and then as we consume the pure ammonia, you can burn it, you can put in a fuel cell, things like this. It's less than the 1,400, it's now 1,200. Okay? So the difference between the two, the ammonia has 87% of the energy that the hydrogen does, right? Sounds bad, right? We gave up 13% of our energy. But this is why you want to do it. To create a liquid with the ammonia, ammonia is almost liquid at atmosphere at regular temperatures. It's almost liquid. It's not quite. So it's going to require about 5% of the energy, an additional 5% to get that ammonia to turn into a liquid. But now that's a liquid, it's energy dense. You can fill up a car with it. You can put it on trains and ships, and it's useful, right? Liquids are much more useful than trying to use gas as a fuel. Gas as a fuel, it just doesn't have any energy density. Your gas tank would take you half a block, right? Now, hydrogen, to turn hydrogen into uh, any sort of density, this is just high pressure. It's not even liquid. To do that requires so much energy. It requires about 40% of the energy in the hydrogen to compress it down to something you can use. So after we turn this into a useful product, the ammonia has 144% of the energy remaining from the start as the hydrogen. Okay. Working with hydrogen is just hard. So chemically, we're willing, it's a trade-off, but we're willing to do it to have ammonia, which is easier to use. Now, sometimes in literature, you'll hear about people wanting to use ammonia as a way to transport hydrogen. And then once it gets where it's going, they're going to take the ammonia and turn it back into hydrogen. And this is something I really struggle understanding the economics of. Ammonia has less energy than nitrogen and hydrogen. It requires energy to take ammonia and to turn it into hydrogen. Not a lot, but definitely some. So on one end, we're going to lose 13% to turn it into ammonia. And then it requires another 13% to turn it back into hydrogen. That, I mean, there's some circumstances where you might want to do that. For example, engine ignition timing. Hydrogen has much faster flame propagation speed. So one of the things they're experimenting with in engines is if you just add a little bit of hydrogen to your ammonia fuel, it revs better. It burns faster. So that, I guess, might make sense to make engines peppier, but you know, to do this to a power plant, I'm haven't come across like the key rationale, right? So just in conclusion, hydrogen isn't fuel. It's a chemical way to store green power. And there are other chemicals that can also store green power. And the reason you want to evaluate different chemicals is the trade-off between the energy to produce it and then the usability, right? Is it in a form factor where you can fill up a ship, a train, a car, or a pipeline or whatever, right? And just doing the head-to-head, ammonia versus hydrogen, it seems like the energy you give up to create ammonia is the lesser of two evils compared to the energy required to compress hydrogen to make it super useful. So there you go. Yes, we don't, it's not the atoms, it's the energy, it's the chemical bond. I hope this makes sense. If you have any questions, write them down. I'm not a chemist, but happy to try to figure this out together. All right, cheers.